week. Okay, on to activity 7, which atom below has the greatest effective nuclear charge. And so as I think of effective nuclear charge from left to right, this is our main periodic trend. Z effective increases left to right. And this is why we have a big difference in property from left to right, is due to an increase in effective charge, and then it resets each new row of the periodic table, but it doesn't reset back to +1 every time. We have a slight increase from top to bottom. So it doesn't increase much from top to bottom, but a little bit. So if I'm constructing a periodic table here, we know that fluorine's going to have a higher effective charge than lithium. Rubidium's, the wrong way. Rubidium's effective charge is going to be greater than lithium's, and then iodine is going to have a greater effective charge than fluorine, and then iodine has to be greater than rubidium. So if we were rank ordering these here, we know lithium would certainly be the smallest effective charge, and then we know iodine is going to be the greatest. So the greatest effective charge will be iodine to answer the question. We might have a tricky time going F versus rubidium here, so it's maybe not clear, which one of these two is higher. It's probably rubidium since it's a left side and fluorine's a right side. So it's probably rubidium. We're not asked to rank order, but if we were, we probably have rubidium than fluorine. But this trend here, not super duper obvious that it has to be rubidium because we know rubidium's greater than lithium, but we also know fluorine's greater than lithium, but fluorine's probably a lot more greater than lithium due to being a right side element on the periodic table. Continuing on to question 2, which atom below has the largest atomic radius? And so our size trend is that our size is going to decrease left to right because the effective charge went up, because the outer valence electrons experience a greater charge. We get a decrease in size from left to right, but then we increase from top to bottom by a fair bit because we're just using larger and larger sets of orbitals. We have a lot more core electrons that repel each other, so our size increases from top to bottom. And so let's reset a periodic table in the proper order. So these elements are kind of grouped in this ordering here. And so which atom is the largest? So our size increases from top to bottom, but it decreases left to right. So lithium's bigger than nitrogen, but then sodium's bigger than lithium. And so we then know sodium's bigger than sulfur. And so for, again, rank ordering size, nitrogen's going to be the smallest of all of these. And I think that's pretty clear because if we compare to oxygen, nitrogen versus oxygen, sulfur is bigger than oxygen. So sulfur's in the third row. We had phosphorus as the choice. I think this would be a little bit more obvious that phosphorus would be bigger than nitrogen, so nitrogen clearly is smaller. So, yeah, I think it has to be obvious here that sulfur must be bigger than nitrogen. But in any event, nitrogen is going to be on the smaller side. And then in the largest side here will be sodium, because we know sodium's bigger than sulfur, and we know sulfur is bigger than nitrogen. And so it would be all the way over here. Sulfur is smaller than sodium, and then we'll have lithium over here. Now, lithium versus sulfur size, this may not be a trend we know for sure. Can we say that for sure? That lithium must be smaller than sulfur? I'm not sure we can make this comparison. I don't know why I'm rank ordering, because the question is just asking for the largest. The largest has to be sodium. That part is clear. I think it's also clear that nitrogen has to be the smallest. I think we need a little bit more information to necessarily be able to rank order those trends. More ion in each pair is greater in size. And so we have a few things going on. We're comparing neutral to cations, so neutral charge atoms to their cations. If we remove an electron, so if we're looking at a 1s2, 2s2, 2p, 6, 3s2, if I remove that 3s electron, I'm definitely going to have a smaller ion than the neutral atom. So if I remove an electron, I always decrease the size. So if I'm going and looking at the radius of, say, magnesium, versus the radius of magnesium plus versus the radius of magnesium 2 plus, I'm definitely dropping in size each step of the way. So losing an electron becomes smaller, no matter what the atom is. And so losing an electron decreases the size of the ion. So the atom that's greater here had to be sodium. Fluorine versus F minus. Now, if we absorb an electron into the shell of the atom, we have one more electron. We go from a 2s2 2p5 to a 2s2 2p6. So we add an electron, we increase the repulsion, so the size of fluoride goes up. So we know cations are smaller than their neutral counterparts, and then anions, of course, are larger than their neutral atoms because we're adding more electrons that repel each other. If I'm comparing same charged ions, so Na0, F0, so uncharged atoms, if I'm comparing uncharged atoms, I use my periodic trends, which would go like this, that we know from earlier, we did this too, that sodium's bigger than, this should be lithium. So sodium's bigger than lithium, top to bottom trend, and then we know lithium's bigger than fluorine, so then we must know that sodium is bigger than fluorine as a result. So sodium is going to be bigger than fluorine. But if you take an electron away from sodium, from here that sodium becomes smaller. So sodium plus is smaller than sodium, but then F minus is larger than F. So if I'm comparing these two here, I'm really making note that they each have the same count of electrons, 10 electrons, but sodium has more protons. So when they're isoelectronic, then we compare their proton counts. When they're isoelectronic, so that makes fluoride bigger. So sodium uncharged bigger than fluorine uncharged, but fluoride charged -1 is bigger than sodium positive charge because they each have the exact same count of electrons. So they each are 1s2, 2s2, 2p6 configurations. And so if you're thinking of the exact same configurations of electrons, the nuclei that has more charge is going to pull those electrons in to be smaller. So sodium smaller, fluoride bigger. So in terms of an answer, which one would that be? Looks like NaF, Na, looks like answer A. What is the general trend and explanation for the first ionization energy of an element from top to bottom? So ionization energy, the IE or the IE1 from left to right, tends to increase due to the increase in effective charge and decrease in size. So left to right trend is an increase. We do see a periodic break in the trend, but this is because electrons are ionized first from their largest orbitals. So we're seeing ionization variation from NS1 to 2 to NP1 to 2 to 3 to 4. So as we go from left to right, we see the NP4 and the NS2 NP1 configurations have slightly lower ionization energies than their preceding element from left to right. So there's a periodic inconsistency, which I'll just label PI. So periodic inconsistency from left to right, not too big of a deal. Is that ionization energy gives us an idea of how attracted are the valence electrons to the nuclei. And in general, they're becoming more attracted as you go from left to right. But as you start to remove them, they're being removed from different types of orbitals and different types of situations. So the ionization energy itself doesn't consistently increase from left to right, even though you can generally think the average attraction of all the valence electrons to the nuclei is generally increasing from left to right. So just a little bit of a nuanced trend on why we see that periodic inconsistency. And then from top to bottom, we have two counter-opposing trends. So we have the idea of the energy, the attractive force between particles that are opposite in charge, kappa Q1, Q2, divided by D. So we obviously want a plus and a minus, but the plus is our effective nuclear charge, and the minus is the charge of the electron. And so the electron charge is a constant. And so the key is from top to bottom, we get a slight increase in effective charge, but the size of the atoms also increase. And so the increasing distance will weaken the attractive force, but the increasing charge will increase the attractive force. So which one wins out? It's usually the size. So usually the size trend wins out for the most case, and we see a slight decrease. So we more often on the periodic table see a slight decrease in ionization energy because atomic size is increasing with that same trend. And so we tend to see the IE1 decrease due to the atomic size increasing with the same trend. And this is despite the fact that we do have a small increase in the effective charge. So from top to bottom, there truly is a increase in the Z effective. So the Z effective, the valence electrons does increase, but that usually it doesn't increase enough to actually increase the ionization energy. For a few elements it does, but for the most part, the general trend is that the IE decreases due to the increase in the atomic size despite the increase in the effective charge with the same trend. It is correct about ionization energies. The first ionization energy always increases from left to right. This is not true because we get a periodic inconsistency with that increase. So this is not entirely true due to that periodic inconsistency that we were talking about on the previous slide. Electrons closer to the nucleus have a lower ionization energies than electrons residing in larger orbitals. And so the closer the electrons are to the nucleus, the higher their ionization energy. So if you're looking at sodium being a 1s2, 2s2, 2p6, 3s1, the easiest to ionize electrons is the 3s. The next hardest electron to ionize is the 2p, then the 2s, then the 1s. So we had talked about the effective charge in lecture at one point that the 1s experiences the greatest charge, then the 2s, then the 2p, followed by the 3s. And so the ionization energies are just going to go with the same trend. So the I1 from the 1s is going to be greater than the I1 from the 2s, greater than the I1 from the 2p, greater than the I1 from the 3s. Meaning, if you could ionize one electron from sodium, but preferentially from these different orbitals, and experimentally it's actually possible to do that, it's going to take more energy to get the electron out of the 3s, or more energy to get the electron out of the 1s, then the 2s, then the 2p, then the 3s. Electrons closer to the nucleus should have a higher ionization energy. They require more energy to be removed because they're closer to the nucleus. You can come back to Q1, Q2, divide by D. If you go closer to the nucleus, the energy of an electrostatic attraction, that magnitude is going to increase. It's going to take more energy. If we divide by a smaller distance, it's going to take more energy to separate, so a higher ionization energy. The 2s electrons in oxygen have the lowest ionization energy of all of its electrons. The lowest ionization energy should come from the outermost shell. The largest shell should be the 2p. So it should be the 2p for oxygen, not the 2s. Have the lowest ionization energy. So that's looking not to be true either. And so which statement is correct? And I'm not sure A, B, or C are correct. Compared to the first ionization energy, the second ionization energy always requires greater energy. And this statement is true. I know sometimes, you're taught like, oh, beware, and the multiple choice question says always. Well, in this case, this is always true. If you take one electron away from an atom, the second electron you take away is always going to take even more energy. Why is this? Well, if you're looking at, say, aluminum or whatever, it doesn't matter what it is. If you're looking at I1, the energy to take the first electron versus I2 versus I3, each successive ionization, what happens is, as you go from removing an electron, the radius of aluminum is going to be greater than the radius of aluminum plus. We're shrinking the radii as we remove electrons. The ions becoming smaller, so the remaining valence electron or the remaining electrons to be ionized are becoming closer to the nucleus, and that becomes harder to ionize. But an electron with the same charge closer in on a positive charge is going to take more energy to remove. Then eventually you get to a core electron. So whenever you remove a core electron or multiple core electrons, that's going to take a lot of energy and a tremendous increase in energy. So you'll tend to see, like for aluminum, without even looking it up, it's probably on the order of, 1,000 kJs per mole to remove an electron. It's probably on the order of about 2,000 kJs per mole to remove the second electron. It's probably on the order of about 3,000 kJs per mole to remove the third electron. Then it's probably like on the order of like 10,000 kJs per mole. A lot bigger increase in energy to remove that fourth electron because that's now a core electron. That's now an electron that's a lot closer to the nucleus than that 3s and the 3p subshell for aluminum. So core electron removal has a big increase in ionization energy. So this statement here is looking to be true. Let's look at the last one. Energy is released by an atom when it loses an electron. i.e. ionization reactions are exothermic. That's not true. These are endothermic. We have to break the attractive force for the electron to its nucleus, so these have to absorb energy. So E is false. Question 6 on electron configurations of cations. Gallium, just to give you an idea, it's element number 31. It's right next to zinc. And so for gallium 3 plus, if I'm thinking of its configuration, I'm probably going to think of gallium. See, let's write a gallium atom first, come up with its configuration. Again, gallium is an argon 4s2, 3d10, and then a 4p1 configuration. And so if I'm losing electrons from gallium neutral, I want to lose the electrons first from the largest orbital, that's the 4p, then the 4s. I leave the 3d alone. In fact, if I'm counting my valence count here, I'd say this has 3 valence electrons, and that this filled subshell, this filled lower energy subshell, doesn't even count towards the valence. So the valence electrons are the ones that are going to be most important to be removed to make cations or to bond with other electrons to make covalent bonds. And so it's going to be these valence electrons that are most important. They're the ones that are removed first, so first from the 4p. We're not asked this, but gallium plus should be a configuration of argon 4s2, 3d10, and the configuration of gallium should just be an argon 3d10. So leave that d subshell intact. If we were asked like how many unpaired electrons, so there's 0 unpaired electrons for the argon configuration in our 3d subshell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons all spin paired. We saw a new word in class today. This would be diamagnetic in terms of its property. Not pulled into a magnetic field, in fact, weakly repelled by a magnetic field. So it should just be argon 3d10. Question 7. Let's do another ranking of size based on an isoelectronic series. Just quick inspection here shows that all these ions have 10 electrons. And so that's going to make the one with the most protons, magnesium, the smallest, followed by sodium plus, followed by F minus. So 12, 11 to 9 protons. And so this is our size trend here for A. Questions from chapter 8 here. So rank the compounds KCl, calcium sulfide, MgO, and MgF2, calcium chloride in order of increasing lattice energy. So the higher the lattice energy, the more energy required to separate the ions. I'm going to go right to the ones that are the highest. That's the 2 plus 2 minus, calcium and magnesium. And so then the next question would be like, so we're kind of thinking these two are probably going to be the highest. Probably in the middle will be the 2 plus 2 minus, or the 2 plus minus 1. And then the KCl, this should be the lowest. And so if I'm ranking the lowest lattice energy, it's going to be my plus minus. And then going to have the next two in the middle be the MgF2, calcium chloride, and then my highest coming next. Let me then start with which one of the two that should be highest, that is the highest overall of the two, and it should be the MgO. Why MgO? It's because its ions are smaller. So smaller ions closer together. So I'm thinking MgO looks like this, and then the calcium sulfide looks like this. So it puts the 2 plus 2 minus further away. So the distance here is higher than the distance here. And so MgO is going to have a higher lattice energy than calcium sulfide. And then the 2 plus 2 minuses are all about a factor of 4 higher than the plus 1 minus 1. And so they're going to be a lot higher than the MgO, the MgF2 and the calcium chloride. And so our MgF2 will come next, followed by the calcium chloride, and then followed by the KCl. And so what's going on here is having a 2 plus has a higher lattice energy than plus and minus, and then plus 2 minus 1s aren't as high as the plus 2 minus 2s. So our lattice energies are kind of in the middle. And then calcium is bigger than magnesium, chloride's bigger than fluoride, so being smaller takes more energy to separate. So for any of these, let's go MgF2, that the lattice energy is the solid ionic compound converting to magnesium 2 plus gaseous plus 2 chloride ions gaseous, and it gives us a strength of the ionic bond. So I'm just thinking here MgF2, its lattice energy is telling me something about the strength of that ionic bond, and then it's generally going to be weaker than those +2 -2s for calcium sulfide and MgO. Here, choose the more polar bond. So the more polar bond is going to be the one that has a greater difference of electronegativity. Negativity of carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine here. And so my um, electronegativity increases towards F. F has the highest. And so we decrease downward and we decrease from left to right, or we decrease away from fluorine. So we're increasing towards fluorine, and then we're decreasing away from it from top to bottom. And so I want to look at my difference of electronegativity. So carbon versus fluorine versus carbon versus chlorine. Which one's going to have a greater difference? Carbon's relatively low electronegativity. Fluorine's relatively high. Chlorine's also relatively high, but not as high as fluorine. So I get a greater difference of electronegativity with CF. And so what this is going to do, if I think of my partial positive and my partial negative, it's going to put these charge magnitudes higher for CF than they would be for CCl. So the CCl bond less polar, the charges at the atoms, the partial positive and negative charge magnitudes not as high as they would be if there was a greater electronegativity difference. ICl versus ICl versus IBr. And so I got to get a bigger difference of electronegativity between I and Cl. So this bond here is going to be more polar, ICl, because I get a greater difference of electronegativity. I don't really need to know the numbers, but if I do, that's fine. This is about a 4.0. This is about a 3.0 for chlorine. I don't have bromine and iodine memorized, but I think iodine's a 2.5 and bromine's a 2.8, if I remember correctly, in terms of relative electronegativities. But obviously, you have to get a bigger difference of electronegativity between I and Cl than Br and I. And so if chlorine's more electronegative, iodine's the least, you get a bigger difference than the element bromine in the middle. And so, again, this is going to mean the charges that we develop on I and Cl should be greater than those on IBr. So the charge magnitudes, the partial positive and partial negative should be greater on ICl. Then NH versus OH. In terms of hydrogen is relatively low in our electronegativity. So hydrogen is, I think it's about 2.1 in terms of its magnitude of electronegativity. Nitrogen's about 3.0. Oxygen's about a 3.5 for N and O. And so, of course, we're going to get a bigger difference between the OH. And so hydrogen, and you can almost think the further that elements are separated on the periodic table, then the greater their difference in electronegativity. And so without even having these values, I think we should be able to predict that the OH bond should be more polar. There's greater separation between those atoms on the periodic table. And so we get a greater difference in electronegativity. And so the NH bond less polar as a result. So more developed higher partial positive charges in compounds with OH bonds and with NH bonds. And so electronegativity of bonds, we're just looking at bond electronegativity, comparing the two atoms in terms of their relative difference of electronegativity. If you had the same atom, if you had ClCl, FF, obviously these are perfectly nonpolar. So these have no electronegativity difference here, so these are perfectly nonpolar. All these bonds here are polar. Now, if you just said, can you tell me if a bond's polar versus nonpolar? Nonpolar bonds don't have a great difference in electronegativity, but the real answer is the only way you can really have a perfectly nonpolar bond is to have the exact same atom bonded with only itself. Okay, so to answer this question would be CF, ICl, and the OH bond. Let's do some Lewis structures. And so pretty basic for O2. I usually just come to a dot diagram for O2 like we did in lecture and just connect and say O2 has to be a double bond. And so for diatomic molecules, usually what we want to do is try to satisfy the octet rule. So for all of these, we kind of want to make sure that we satisfy the octet rule. Is going to be one thing for diatomics. And we don't necessarily strive to always satisfy the octet rule for larger atoms, but when I get to nitrogen, I can satisfy the octet rule here. And so I come up with a triple bond for N2. We get a lone pair on each nitrogen, so nitrogen, nitrogen, lone pair, lone pair. And so if we're counting lone pairs and we're counting where the bonds are, we can also think of calculating the formal charge, 0 and 0 here. For carbon monoxide, Now, how do I do carbon monoxide from a dot structure is actually a little tricky to kind of comprehend. So an easier starting point for CO, I think, is kind of recognizing that you have the same count of electrons as nitrogen, as N2. So if we're going to have CO satisfy the octet rule, then we kind of only have this choice here of Lewis structure. And so there's really no other Lewis structure I can write that both satisfies the octet rule for both atoms as a kind of rule of thumb. So this is our best Lewis structure for CO because I have 8 electrons around carbon, 8 around oxygen. But then if I think of my formal charge of carbon should have 4, but it actually has 5 electrons closest to it. So this actually makes carbon a -1 formal charge. Oxygen here should have 6 electrons surrounding it. That's its valence count, and it only has 1, 2, 3, 4, 5. So it only has 5, so it's a +1. And being +1 is just what its formal charge ends up being. So -1 + 1 = 0. So carbon monoxide's net neutral, so the -1 + 1 sum up to neutral. But this is what the Lewis structure of CO looks like. So it's a triple bond. The carbon actually bears more of the negative charge than oxygen does. Now, when we talk about electronegativity, oxygen is more electronegative. It's going to try to pull those bonding pair electrons closer towards itself, and it does do that. And it actually, as a result, comes up with a lower positive charge than +1, but it's still positive, and the carbon in CO is still negatively charged. And this is actually kind of what ends up making CO so poisonous in our bodies, is when we breathe it in, the carbon will attach to hemoglobin, which on the surface you may say, well, what does that mean? Well, that's kind of what O2 does when you breathe it in. You breathe in O2, O2 attaches to your hemoglobin in the lungs and takes it to the heart and takes it to your body, and the body can remove the O2 from the hemoglobin, use it, and then myoglobin takes the CO2 back to the lungs where you exhale the CO2 that the body has produced from. Think of how all the combustion reactions inside of your cell are producing CO2. They're using O2 as their source. They're just doing oxidation reactions, just doing the combustion reaction. Just imagine the whatever plus O2 goes to CO2 and water. Well, the CO2 is fed back to your lungs, reversibly binds to myoglobin, so then it can be removed very easily. Now, what carbon monoxide does is the carbon, that negative charge, actually binds to hemoglobin, just like the O2, just like oxygen does, but it does so irreversibly. So when carbon monoxide binds to your hemoglobin in your lungs, it's pumped through your body, and now your hemoglobin doesn't have O2 to give the cells that it needs. It has the CO molecule attached, and that CO molecule doesn't come off. So the only way that you survive a carbon monoxide poisoning event is to get the fresh air quick enough for your body just to recycle and remake new hemoglobin. And if all of your hemoglobin is attached by carbon monoxide, it's very unfortunate, but that's going to lead to that leads to death. And so it's very interesting, I think, here to be able to consider what really makes CO special is that it's going to bind hemoglobin through the carbon atom. And it's because the negative charge in that carbon atom, just as virtue of its Lewis structure that we see here, that leads to that effect. If it somehow had a more negative charge on O, it would have binded through the O and probably would have been a reversible step, because the oxygen in O2 binds reversibly, but the carbon in CO binds irreversibly to hemoglobin. So anyways, I think it's a very interesting story that you can tell, and CO is a very fascinating molecule in that regard. And it's also an interesting case where you see a molecule that's stable enough to exist that doesn't have zero formal charges across all of its atoms. We could look at an ion like ClO minus, and this isn't too confusing. It's just a case where you take chlorine, has 7 valence electrons, the oxygen has 6 valence electrons. We add 1 in for the charge, gives us 14 electrons. So this looks much like the Lewis structure of Cl2 or F2, other molecules that have 14 electrons. So it just looks like ClO, and then I fill my octets around each of the atoms, just like Cl2 or F2. So this is 14 electrons distributed, single bond. So notice for CO and for ClO minus, I kind of didn't really go to a Lewis dot diagram. I just kind of counted their electrons and then figured out, well, what would be the right type of structure. Single bond for 14 electrons. If I had 12, there's no example here with 12, other than O2, I guess, has 12 electrons. So 12 electrons would go double bond. When I have 12 electrons, if I only have 10, I go triple bond. And so now where's my charge in this molecule? Break the bonding electron in half. Let me do this in a different color. So I have the bonding single bond electron cut in half. So I have 7 electrons for chlorine and then 7 for oxygen. So oxygen should only have 6. For a neutral charge, it has 7, so it has a net -1 formal charge. And chlorine here is neutral. It should have 7, and it has 7. And so that's our Lewis structure for ClO minus. Can we calculate just some formal charges here of these two different Lewis structures we have shown for the phosphate ion? And so for the phosphate ion, let's calculate the formal charge of this one first. So that phosphorus has 4 electrons closest to it. Phosphorus is in the row of nitrogen, should have 5 valence electrons, and it only has 4 electrons surrounding it in this structure, giving it a +1 formal charge. So I'd write a plus sign here for phosphorus. And all those oxygens should have 6 electrons surrounding them for a neutral charge, but they have 7 electrons surrounding them. So that's -1. You could come back to by rule, the valence count for the atom, O is 6, minus all the non-bonding electrons, and then -1/2 the bonding electrons. And so there's 2 electrons in that bond. I'm just breaking it in half. This breaking in half is what I do with the box. So I'm kind of doing the breaking the electrons in half by drawing a box and doing the math this way. That's the way I like to do formal charges. I think it makes a lot of sense. You just draw the box, you keep all the non-bonding electrons around a given atom, and then half the bonding pair electrons. And so that gives us the formal charge of -1. And so I could write minus for all these O's, do a quick double check that I have 4 minuses, and I have a plus that equals -3, which is the charge of phosphate. So that's perfect, that's good. I should be able to sum up all the formal charges of the atoms and calculate the charge of the molecular ion. This is PO4 3-, so that checks out. And so then that's the formal charges for the one on the right side. The structure on the left side has formal charges 1, 2, 3, 4, 5. So let's break the bonds in half. I'm going to explicitly show all of the bonds being broken in half just so we're clear that 3 of the oxygens look like they did in the previous structure where there's 6 -7s for -1. So I have a minus here, a minus here, and a minus here. But this oxygen here has 0. So it has a 0 formal charge. And then phosphorus is also 0. I'm usually not concerned with showing the 0 charges on a Lewis structure. I'm more concerned with showing the non-zeros. But you can see here I have 3 minuses and then 2 zeros. So that 3 minuses sums up to the overall charge of -3. And so these are just how we can calculate the 2 sets of charges on these 2 different Lewis structures for phosphate. Now we're asked here, which one of the Lewis structures violates the octet rule? The octet rule is violated by, let's call this structure A. So structure A violates the octet rule because the structure has too many electrons around phosphorus according to the octet rule. So if I look around the entire structure of phosphorus, I have 10 electrons. So I got 2, 4, 6, 8, 10. And the octet rule would say that there should be a maximum of 8 electrons around that atom. Now, in some regards, we will see a lot of Lewis structures that violate the octet rule. This could be one of them. Which one minimizes formal charges? That is also structure A. So structure A is minimizing formal charges because it has these formal charges being minimized down to 0 through making the double bond. So should we minimize formal charges through expanding the octet? The textbook suggests that, well, if you do so, that leads to what you might call the formal charge rule or a Lewis structure that shows those formal charges being reduced. Now, if you look at any modern, theoretical modeling that you can look at molecules like this, if you look at the nature of the orbitals of these molecules, there's fundamentally no way you can make that double bond between P and O that makes any kind of sense that I can make sense of, at least. And so I think structure B is probably the better structure that more resembles the real molecule. So expanding octets, probably not something that really happens, but really the point of this example is just to calculate and compare their formal charges, which we can do so. And let me go through one more example with PO4 3-. Let me switch colors here. If I wanted to sketch this Lewis structure, and if I had said determine and sketch this Lewis structure, the way I would go about this is I'd count up the valence electrons. Phosphorus has 5 it's just based on its row in the periodic table. Oxygen's 1 over, so it's 6 for each of the 4 O's. I have to add 3 more electrons in for the charge into the valence shell, so that gives me 32 electrons. And so if I'm sketching my Lewis structure, if I'm trying to come up with those structures above, I kind of start with single bonds. That was kind of our Lewis structure rules are count up the electrons, kind of identify the central atom, which honestly is really easy in almost every structure we give. It's just the first atom's the central, and then all the other atoms are attached to it. And then we complete the octets of the non-central atom with lone pair electrons. And then we count our electrons used at this point. That's 32 electrons. If I had any electrons left over, I'd put them on phosphorus, but I don't have any left over, so I don't have any electrons to spare. That also means when I'm looking at a Lewis structure, I should see the 32 electrons. Like on a test, sometimes we'll say, you know, for a given structure, which Lewis structure is right or wrong for a structure. The most basic thing you can do is count the electrons in the Lewis structure, and if they're mismatched, then it's the wrong Lewis structure. Like if I show you a Lewis structure for this molecule here, let me sketch these to be a little bit more clear. Let me say I show you a Lewis structure, and I just happen to take 2 of these electrons off here. Like I just removed 2 minus charges. That can't possibly be PO4 3 minus. And that might be a representation of PO4 2 minus, but it's not even going to be the right one, or excuse me, PO4 with a minus. So like we have to have 32 electrons, and if we don't, it's the wrong structure. So let me put these back. So if you're asked right or wrong Lewis structure, the most basic thought would be count the electrons that should be shown in the structure and see if it's correctly shown in any of the structures. And so for this Lewis structure here, then, is this the best Lewis structure? Well, that's where you, in my opinion, you calculate formal charges. You then think that you can try to minimize formal charges by making multiple bonds, but you shouldn't really expand an octet to do so. But if you do so, you would at least stop at, you know, the 0 charge on the atom. So if you want to move these electrons in to make this double bond, and then in the process you're reducing the formal charges of those, that you need to stop at 0. If we try to do this again, that's going to be bad because we're going to make phosphorus now negative and oxygen 0. That's no longer decreasing magnitudes of formal charge. So at least if you do want to use multiple bonds, we have to stop at 1. And then lastly, if you did make the 1 double bond, if you're looking at structure A up here, then somehow we have to picture something called resonance. That anytime you have multiple ways of sketching that Lewis structure, like where you could have said, well, why don't I put the double bond here instead of here? I know the structure is kind of messy. Let me erase some of this work here. But if I'd said, well, why don't we put the double bond here instead of here and swap the double bond out? Or why don't we put the double bond here instead? Or what if we put the double bond here? Well, anytime you have a case where you can sketch multiple Lewis structures that are identical in their appearance and what they're representing, the real molecule has to exist as the composite of the average. So in other words, no matter which of those 2 Lewis structures, A or B, you're looking at, somehow in your mind you have the picture that really, truly, all 4 of those PO bonds are identical to each other. So we really have 4 identical PO bonds, even if one Lewis structure looks like we don't. So that's the concept of resonance. A little more in some lecture examples, but we can get into those topics here in this video. Let's look at one more Lewis structure question and then wrap this video up. Obviously, I don't think you're going to necessarily get too far in the recitation activity, which is okay. I mean, I like making activities that kind of give the class a chance to see a bunch of different problems and to really let your TAs kind of fine-tune where they think they need to spend more or less time. If you make it this far in class or made it this far in recitation, that's great. If not, maybe this is just another example for you to kind of hear me talk a video and show you how to do some Lewis structures. And so just look at the lecture slides that go through the rules, or your textbook that goes through the rules. And for each of these, kind of start by counting up the available electrons. So it's 24 for BCl3. PF3 would be 5 plus 3 times 7. That's 26 electrons. SiCl4 would be 4 plus 4 times 7. That's 32 electrons. 1 plus 4 plus 5. That's 10 electrons for HCN. ClF3 is 7 times 4, that's 28 electrons, and ClO4 minus would be 7 plus 4 times 6 plus 1 for the negative charge. So I have to add 1 for a negative charge. If we ever have a plus, we're taking electrons away from the valence shell. but this will give us 32 electrons for ClO4 minus. And so in terms of their Lewis structures, so we got BCl3, chlorines, that's 24 electrons. And so we're good for BCl3. No lone pair for boron, that's okay. If you want to do this, this is wrong. Why is this wrong? 6 electrons, not 24 electrons. So this might be what you'd sketch for BCl3 2 minus, but not for BCl3. And it turns out actually BCl3 2 minus is not even really a stable ion. It's not really something that's all that important. So this isn't even really something that forms. Let me also take a sidetrack to say we're not showing you Lewis structures so that you can then tell me why compounds exist or don't exist. Why is one formula more stable than less? No, no, no. It's more like if I give you a formula, I just want you to sketch the Lewis structure. And if we see enough examples, you can probably start to see some patterns of stability. But I just want to be able to show you, go from formula to Lewis structure. That's basically the key here. So BCl3 would be this Lewis structure here. And then if we try to make multiple bonds, if I try to do this, this doesn't work because I'm increasing magnitudes in charge. I'm taking what was a 0 formal charge. So we started here, 0 formal charges all the way around, 3 minus 3 for boron, 7 minus 7 for the chlorines. So they're happy, if you will. Boron has the right charge. Boron is not a very electronegative atom at all. The nucleus does not have a strong pull for electrons. It's not going to be able to pull an electron pair in off of chlorine, which is a much more electronegative atom, and really actually wants boron's electron more than it wants to give boron one of its electrons. So if you think of the relative pull here, chlorines are actually pulling electrons off of boron, and boron should be partial positive in terms of its charge. Clearly not negative, partial negatives in terms of the chlorines. PF3, so PF3, fluorines around phosphorus. I should mention that I don't care about geometry here. So the way I sketch my fluorines, I really don't care if I'm going to put them in this order. I could write this, maybe this way. I am not trying to portray anything about geometry here. So I really don't care to sketch Lewis structures any particular way. So let me just go back to the initial way. We sketch it here, lone pairs around the fluorine. Let's count the electrons here. So this is 24 electrons used. So that leaves behind 2 electrons left over. These 2 electrons here that are left over are placed onto the phosphorus atom as lone pairs. So PF3 gets lone pairs, and it's just because phosphorus, by virtue of being an element that has 2 more electrons, gets lone pairs on it, where boron didn't have those 2 electrons to place on it. But boron was okay, because if I put 2 electrons there, it's now putting more electrons around an atom that doesn't have the charge to really hold on to them, if you think about it. Phosphorus needs those 2 electrons because if it doesn't have them, it then has a big positive charge, and it's going to want to go try to find electrons off of something. So it's really just about charge balance. So if we think about phosphorus here, it satisfies the octet. If I think about the formal charge of phosphorus, I then break the bonding pair electrons in half. So the formal charge of phosphorus is 0, the formal charge of the fluorines is 0. Now the real charges, like in fluorine, are going to be partial negative because fluorine's more electronegative. It's going to pull those bonding pair electrons closer towards itself, go partial negative, and the partial positive charge truly on the phosphorus. SiCl4 is a lot like CCl4, just silicon, 4 chlorines. On the chlorines, that's all 32 electrons. So when I get to a Lewis structure and I have 2 things going on, I have an octet around the central atom, and I also have a 0 formal charge around the atom. Both of those things are really good for that Lewis structure being done and nothing else being possible. So when I get 0 formal charges all the way around, even when I'm violating the octet rule, I just see that, well, that molecule is just going to violate the octet rule. That's just the way it is, and that's okay. What about HCN? Now, for HCN, and now HCN has a slightly different issue here, which is that I now have a 2+ formal charge on HCN. So this is just following the rules, where where H to C to N is the connection of the atom. So carbon's my central atom just by that connection. And then in terms of electrons being used, 2, 4, 6, 8, 10. That's all the 10 electrons I have available, so none left over to go onto the carbon atom. And so now if I calculate my formal charge, carbon should have 4, it only has 2, so that's a +2. Nitrogen should have 5 in terms of its formal charge, and it has 7. 1, 2, 3, 4, 5, 6, 7. And so I'm just breaking all these in half, 1 minus 1 for the oxygen being 0. So now, to me, I like Lewis structures that help us see the simple interaction of negative particles with charge is that this 2 plus charge can pull these electrons in to make a double bond, reducing this down to plus. I remove these electrons here, it takes this formal charge from -2, now down to 5 minus 6 for -1. And so let's do it again. And so let's not use that one. Let's use these electrons here. Let's move these in here and reduce that formal charge now down to 0. Let me rewrite this as HC triple bond to N, lone pair left on N. And so now what does this do here? Well, now I have, through this triple bond, that I can see how I get to it. I have nitrogen with a 0 formal charge, 5 minus 5, carbon with a 0, 4 minus 4, oxygen 1 minus 1 for 0. So HCN, triple bond to N. Now, this might be something more we focus on in Chapter 9, but you will see, you'll focus on this a lot in OChem if you take 2510 and 2520, is that carbon forms 4 bonds. It's going to form either 2 double bonds like CO2, it's going to form a single and a triple like this molecule here, it's going to form 4 single bonds like in CH4 or CCl4, but carbon's not going to form with 5 bonds, not going to form with 3 in stable molecules. So like we want 4 bonds to carbon, and that gives it a neutral formal charge. Nitrogen likes to form 3 bonds, either a triple, 2 singles, or a double and a single, but with a lone pair on nitrogen. That gives it a 0 formal charge and satisfies the octet rule. Okay, so let's look at ClF3. And so some molecules violate the octet rule for having too few electrons, like BF3. ClF3 is going to do the opposite. If I start with ClF3, by rule, find my central atom, chlorine, attach the 3 fluorines, complete the fluorine octets, then count my electrons used. That's 24 at this point. I only have 4 electrons left over. Where do they go? Well, let's put them onto the chlorine atom. And again, I really don't care where I put them other than I start to run out of faces on the chlorine, so I kind of just put them off to the side here. We'll talk in Chapter 9 about what the actual molecular geometry of this molecule looks like. But for now, I'll just leave it as this. In terms of electrons being distributed, that's all 28 electrons. Let's calculate some formal charges. So let's break the bond pair in half here. So that gives me a 7 minus 7 for 0 for the fluorines. So if the fluorines are 0, the overall molecule is 0, so chlorine has to be 0. How is the formal charge of chlorine shown to be 0? Well, I take all the non-bonding electrons, so the 4, so I'm going to put those in blue. So I have the 4 non-bonding electrons, and then I have the 1, 2, 3 bonding electrons, so that's equal to 0. So chlorine's formal charge is 0, fluorine's is 0, and ClF3. But now the chlorine has an expanded octet. So if I look at the chlorine atom, chlorine has an expanded octet because there's 10 electrons. So we have an expanded octet for chlorine. That's okay. That's just the way. This is a real molecule. This thing exists. You can buy that chemical. BCl3, also a real compound, also stable enough to exist. But it has a deficient octet. So these are octet rule violators. That's okay. Now, how does ClF3 really survive as a molecule? It survives because the fluorines are pulling electrons away from the chlorine, making room for those extra electron pairs on the lone pairs. We'll see things, that's not one of the things, but SF6 is another compound. You put fluorines around sulfur, and this molecule here exists a stable molecule. So SF6 is happy. Lone pairs, I'll just show up around one of the Fs. So all the Fs have lone pairs. But this molecule here exists. You can actually, I don't like doing this demo, so I don't think I'm going to do it, but you can actually breathe in SF6. It's such a heavy gas, it makes your voice deeper. Um, Unlike helium, being a lighter gas, makes your voice higher pitched. SF6 makes your voice very, very deep sounding, kind of naturally, just like helium does the opposite effect. But the point for SF6 would be that you have all these electrons here. You have 12 electrons around sulfur. How does sulfur exist with 12 electrons surrounding it? Well, it does so because fluorines are pulling electrons away through being very electronegative. So I think we'll talk about that molecule a little bit more in chapter 9. But one more example for the set here is ClO4 with a minus charge. So ClO4 minus. So for our last example, central chlorine. This is the perchlorate ion, if you recall from nomenclature. I think I said perchlorate, but making sure I said the right suffix, perchlorate ion. And so we have oxygens completing their octet. That's all 32 electrons. And so I now have a big formal charge on chlorine. I have a 3+ formal charge on chlorine, minuses all the way around. And this is really a good stopping point for this video and for the chlorate ion. We could minimize the formal charges and make double bonds, but I don't think there's really much. I mean, let me show you that structure. I guess we'll wrap up there. But if I take this structure here and just make 3 double bonds and leave the other one single, if I do this is still 32 electrons. You can count and double check if you want. But that's still 32 electrons. I'm just making double bonds here to reduce the magnitude of the charge down to 0, 0, 0, 0 for chlorine, -1 for the 1 oxygen. And so the formal charge there is still -1 overall, but I've just minimized the magnitude of formal charge. Now, if we're calling this Lewis structure A and this B, I think A is the better Lewis structure. I think B is categorically a worse representation of the molecule. But if you picture B, somehow you got to picture that thing resonating, and that the key to me would be, no matter which one you think is best, A or B, I hope you see that all the bonds are identical still through a concept called resonance, which we didn't talk much about resonance in this activity. We'll talk about it more in lecture. But through resonance, all those bonds would have to have the exact same bond length, the exact same properties as each other for whether you're looking at A or B. It's just a little bit harder to see it in B than it is A. Okay, so hopefully this packet here helped you conceptualize structures, Lewis structures a little bit better. And whether or not you're just hearing it in the video and didn't get to see this much in recitation, I guess we'll see how this week goes. But to me, Lewis structures should be something that are pretty easy once you get the hang of it. And if they are something that's continuing to be a struggle for you, let's go back to the rules. Let's go back to a bunch of examples. Let's try to work together to try to understand how to sketch Lewis structures. As we get into the next chapter, we really have to be able to sketch a Lewis structure, or a lot of the aspects in the next chapter won't make a whole lot of sense. All right, so that's our video. Definitely went long on the video, but again, hopefully this is a good resource for you to use, in addition to your recitation class. All right, guys, have a great week.